Let's talk then about another equation of state briefly. The compressibility factor equation of state is a really simple improvement on the ideal gas law. It's also going to relate PV over T, but it's going to take into account this observation that all the chemicals have kind of similar patterns to the data. So this graph that I've shown here is pressure versus temperature for a typical fluid, where we have liquids and gases at various shapes, and we're really trying to model what happens to the gas region. The compressibility factor is going to be one way of dealing with non-ideal gases. So if we have the ideal gas law, right, the ideal gas law says PV equals nRT, or P little v equals RT. But if this is not true, then we can quantify non-ideality as the ratio of PV over nRT, or equivalently P little v over RT. So this is Z, and it's called the compressibility factor. For an ideal gas, Z is going to be 1. For other substances, it won't be 1. So what is it? Okay, well, a lot of times we can look these values up, and they can be found in things like the Perry's Handbook that we had talked about earlier. Many of the equations of state can be rearranged to solve for Z, and that's been done in this and many other textbooks. We can also use something called the law of corresponding states to estimate Z. So what is the law of corresponding states? Well, the law of corresponding states is a requirement that all substances, if they are scaled so that they all pass through the critical point, and you were to stretch and squish diagrams of their data so that they all pass through the critical point, and in this particular case, that critical point is right here, okay, then all substances have graphs that end up looking fairly close to each other. Now, this particular graph is the one that is just for temperature and pressure and compressibility factor. But there are many other forms of the law of corresponding states, and we cover those in some other courses. Now, the way this works is we calculate the temperature and pressure as compared to the critical temperature and pressure. Those are called the reduced temperature and reduced pressure. Reduced temperature is going to be designated T sub lowercase r, and it's T over the critical temperature. P sub r is the reduced pressure, and it's P over the critical pressure. Now, key to this is that these must be absolute temperature, absolute pressure, and these are going to be dimension-free. So in other words, if I'm using degrees Kelvin for the critical, I have to use degrees Kelvin for the actual temperature. Similarly for pressure, I use atmospheres for both or kilopascals for both, but I have to make sure that the units cancel. Now there's also a reduced volume, which is the actual volume times divided by what one would get if you calculated the volume at the critical point for an ideal gas. So that's V times PC over RTC. Now this is going to work for all substances except for the two tiniest, and that's hydrogen and helium. For hydrogen and helium, you're always going to correct the temperature and the pressure for the critical by adding 8 Kelvin or 8 atmospheres. So in other words, if you have hydrogen and you wanted to find the reduced temperature at some temperature, okay, you're going to take that temperature and divide by not the critical temperature of hydrogen, but the critical temperature plus 8 Kelvin. And the pressure, you're going to do the reduced pressure by dividing by the actual pressure divided by the critical pressure plus 8 atmospheres. So hydrogen and helium get this special little extra step here because they're so tiny they don't really follow the rules quite as well as the others. Now there are graphs for Z versus PR for a variety of temperatures, and these can be found in the textbook. The graph that I will be demonstrating is the one shown here. I've selected to do my examples using this one because it is the most challenging of the versions of the graph to read, and it is one that is commonly used in many textbooks in your future. Now sometimes we need to work with mixtures of gases, and we've talked about an ideal gas mixture, which all the gases follow the ideal gas law and they behave ideally with each other. We want to be able to talk about gases that are not ideal. So one of the easiest ways to approximate models for gas mixtures is to use what's called a pseudo-critical point. Now this is not something that you will ever be able to measure, okay? But the pseudo-critical point uses the gas molar fraction, so the Y is the mole fraction of I, and it's going to use weighted fractions of the temperature or the pressure to calculate a pseudo-critical temperature of the mixture or a pseudo-critical pressure for the mixture. Again, for hydrogen and helium, you would add 8 Kelvin or 8 atmospheres to the TCI for those. Once you have this pseudo-critical value, then you're simply going to use it like you would for a normal gas. You just can calculate the reduced temperature as T over Tc, but it's that pseudo-critical temperature. And similarly for the reduced pressure or the reduced volume. It's not going to be a particularly accurate approximation, but it's quick, and everything else that you can do is very definitely not quick. It's going to be covered in future thermodynamics courses. So this is going to be really the only easy approach that would be a first level calculation so that you would have a rough estimate for your answer.